The pre-version for the longer one, it's 1 hour long, but this is to give you an idea. We're going to look at this fracture test, and I want you to think of it as a full deck. Dimensions are actually pretty close to what we're dealing with, this fracture sample, but just looking at a dissection of it and behavior, I want you to think of the top, this blue bar right here, as our tension steel. So I'll change it to orange. That's our tension steel. Our tension steel that handles the negative load across the top. And here's our tension steel that handles the deflection down the bottom. So as it deflects, this becomes in tension. So it works not all the way over, roughly about 25% back, about there. Let's just use that as a scale to show you about photography and how things mess up. I want you to look at this yellow line here. It looks in line with the corner there. As I grab it and I move it over to the other corner here, you can see how far it's off from there. They just don't line up. As you can see now, that's way off. Look at the space there. It lines up in one position right there. So keep in mind, you're dealing with converging lines from the photography. This piece represents where it's no longer concrete engaged at the steel. If I were to drop this back in, it would be that piece, the continuation. Moving it out of the way, just so you can remind yourself what you're looking at, is that it's now acting as that staple that I showed you when I did the staple and I went down and around and back up into the concrete. This is acting as the staple, just a straight piece of steel across there. But it is locked here. This is where your hooks come into play. The hooks, the hooks you see that they talk about, or the L-shaped 90s, they act as anchor points. And for some fracturing like this, it will help it stop from slipping because of this 90, this anchor, if you will, this embedded anchor. So that's not. I'm not saying it's an anchor down there, but it's enough to keep the pull out. It's enough to keep this from fracturing. In the 1 hour video, you'll see longer. You'll see it over here, 1 hour and 8 minutes. This again is the pre-video to that. What I want you to visualize is a vehicle. Let's see. Can I do my car? So it's gonna be kind of hard to do a car, right? So car, and there's my car. If the car is over here driving and stopping as it loads down onto this deck, it puts the load as this steel is compressing down. It puts the load there. It wants to cause this fracture as you're looking at it. The fracture, it's in tension. It's trying to make it all the way over to here, and it resolves itself in this capacity first here, fracturing here, and working its way back to the actual load point. This steel right here. We'll delete that. Working its way back there. At that point, it wants to deflect down, but we do have some steel that even though the top steel is referenced as going into tension at that point, it's still the compressor side. It's actually resisting the other direction also as it's trying to go down. It's actually resisting two directions initially when it's trying to push out. And then it does a reversal as it fractures. As this fractures and goes down, we get this bow like this, right? Let's call it a little bow. And that's really emphasized at the bottom. The bow is like that, and this metal really gets deflected. It really gets deflected. This metal also gets deflected. I'm going to use that point there. From here to here, it spalls off. You can see the fracture right about here ready to pop off. You'll see it in a longer video. You can see the deflection here. This is that loading here, the vehicle loading here. And that top steel is our tension steel, our steel that ties back into the wall, but does it. In our wall system, it seems like the steel is low. I could not find the high steel, two layers of steel, and one of them being high at the wall. I keep finding this low steel. The low steel would be an anchor point, a lot of compression here, but with nothing to help grab it. Let's see, grab it. Well, okay. grab this load from the bottom to stop it from deflecting and put it back inside this tension steel, which would be anchored into the back of the slab, not anchored any further, not anchored back further than the end of the slab. There's nothing like this there. Now, to stop this from opening, you use stirrups. They don't use stirrups in decks, all right? Stirrups aren't really used in decks. What they do in some countries, they'll use a crank bar, which that's like that. The crank bar the bottom steel is integral with becomes integral with the, let me go down here, integral with the top steel, and it helps with, it looks like that. It helps with the shearing action. And see how this, so let's remove these. These were here, and this would have helped with that, maintaining the bottom from trying to move away from the top. It ties them together. The steel putting it in tension that way, so it can't separate. We remove these, and you can see where this crank bar would have come across, and it would have worked in this capacity, where it's coming across our line here. These are called crank bars, and that's the way they work. Now, there's not just one crank bar there. They're spaced 12 inches all the way down. So this really helps work better than what we do in the United States, where we just use top layer in that tension area and then the bottom steel, and we don't do stirrups. They would be kind of odd. You'd think they would be able to manufacture them in loops like that. That would be very smart. Or use crank bars, and we don't do crank bars here. So this is a beautiful thing there. Without this, you're looking at the fracture as it would happen. It would load here and create this fracture. On the car garage video, which I show, we see this fracture at the north wall. We see the column like this, and let me just do that for column, and then we see this 45 right here, this piece over there hanging in the air with two pieces of bar sticking out of it, parallel with the perpendicular to the south wall. Parallel with the other column. There's two columns. It's just in line going back towards, between the trucks, the truck and the vehicle, back towards the structure, not shifted one way nor the other. It's pretty much parallel. So we have this here. So that indicates we have this. Now we have that planter box over there. Our planter box, let's get rid of these. Our planter box is part of this section here. So if I would put the planter box, I would put it here, above, on top of this section here. Then we get our car loading, and we can get a lot of loading continuously. And right about here is where the fracture happens with the planter box, the rotation. So we can get this going down, but not at the wall, but out at the edge of the planter box where it has a natural tendency to want to fracture far out. Even though the load's way back here, we see the crack here, it works its way back to where the load initiated from. That's the way these fractures work. So we have a planter box with a point load there. We have our vehicle load that's always coming in, loading and stressing. We have no shear links. We have no crank bar detail. So we start getting this crack. We do that. It transfers over from one, I want to say bay, but one section all the way over the entire length of that planter box. And we've got a significantly weak section going across. I don't believe in coincidences, and that's right where the planter boxes are, where we have our break. Our break is right about where the top reinforcement would be, as I stated. I don't know if that top reinforcement is there. If it's not, and there's no top bar there, there's no top bar here like this, then we just have this bottom reacting in this capacity. And I have looked at research with no bar there at the top. We still get the fracture thereabouts, looking like this, and grabbing, and then there's your grab moment. So even without the top bar, you still get the end result like this. And it would be beautiful if we could see the fractures. Was there one at the wall, and was there one out here? This would look like that pull away. This creates a pry bar effect. And now, per the ACI code, they call it pry not pry bar. I call it pry bar. They call it prying something like a pry bar. Pry. Okay. Pry bar, pry something. I'll do it in the comments for you. It's equivalent. It's the same thing as prying out, pry bar, pull out. It creates that effect against that wall. There's your wall. As this goes down, it can pry out the steel that was whatever was engaged with at the wall, creating that shear plane. You look at the shear plane there, and sometimes we don't see rebar. All right, over there, and sometimes you do. Perhaps some of the rebar was further back, but perhaps you did have cover, cover for the steel. So maybe the cover went to there, and what you're looking at that's left without cover is concrete in the wall. And when the pry bar effect happened, it just fractured this, no problem. And we get that clean fracture that what it presents is no rebar there. Some places we do see the rebar, so it had better engagement. We do see, I saw rebar in many places. I know it's, but I haven't really seen it high. I've only seen where peers looking at that wall system. Here's the wall, the block wall above. Looking at that wall, I see the layer where the patio was installed, including the pavers. And then below that, I see what appears to be the concrete deck, which is here. I don't see the rebar. Let's do a circle here. I don't see the rebar high. I see it right about near the bottom of this area over here. I don't see a secondary line of rebar here above it and all the way down. I'm only identifying one line, which is just the bottom rebar, and over at the wall I'm not identifying the top rebar that would help grab this intention. Remember this as I end it. Here is let's call this the beam. Let's see if I can colorize good. I'll leave this up like that. Let's change the color to help you ease out. So here's the beam. Your steel would look something like this. I mean the floor. It would look something like, okay, that's nice. Maybe I got to come out here. Yeah. So it would look something like this, about 1/4 out. Let's do 1/4. And then let's do the full length on the bottom one. All right, let's just do the full length. And you can go beyond it a little bit. And you come this one. When I say full length, I think they were dealing with 20-foot bars. And this is about 23 foot 6 to there. So it actually, I've been thinking about if they had 40-foot bars. I didn't see them spec it. I actually saw them spec 20-foot bars. So if this is 23, you want to stay out of the tension zone. So we can go from here to here. We're not going to put a scrap down there. And we would put that there. And then the next piece going over, you would overlap it. It requires 30 times lapping. So you would overlap like that, butting going right next to it. Overlap with a zero, let's say zero tolerance, meaning it's wired together. So let's just do that. And there's your continuation of your bottom bar. So as this deflects down, I don't know what they allowed for right then. I'm still working on it. The 300th or 1/500th per the span, which comes out to about 0.9 inches, 0.9, 9/10 of an inch. How's that? About 9/10 of an inch of deflection allowed for before it's now too stressful. All right, how about that? So the steel, this tries to deflect, and when it tries to deflect in the middle here, this can handle it. It tries to deflect. This grabs it from going down any further because it's engaged. In this case, engaged across a column head. So the column head is here. And that continuation would, that continuation would be over top of it like that. And it goes over across the other side. So that would help it from deflecting down as it's grabbing the tension. It's just trying to sag down. It's like an arm reaching out of your shoulder, holding it up. And over here, the same thing, except for there's nothing anchoring it back besides its own load, dead load. Hold on. What else is anchoring it back is these bars right here. The bars look like this. And if those bars aren't there, let me end that call. Okay. Good. All right, so it would be these guys here holding this down, and that stops it from that. So it really matters about these guys on this side. And on this side, it's kind of in equilibrium with the load, the opposite loading. And also, this has what we saw, the 14-inch, I call them rabbit ears, right? We got the 14-inch rabbit ears over here that also, I bent that one down a bit. So that one is also holding. The bars held, as we saw. Some of them, when this went down and the bars bent over, it spalled the concrete off right here. But I think there's only one bar that's missing out of all of them. I think I saw it looks like it snapped off. Just one out of all of them. You can see the intent. Again, it's like an anchor to hold this back. So it's just trying to dip down. This is doing that. So if you get these failing, now we got a different dynamic. If we get these 90s failing, I really don't know. All those holes we see over there, they could be the 90s we're looking at. I don't really see the double hole, if you will, like the rebar came over, tied into these 90s. It's like, I know the photograph's so far away, and I wish somebody can get closer images. And I know we have some close, but there's still not enough to tell dimensions of the rebar. I'd love this for you guys to look into that hole and find double rebar. Go, look, it's right there in front of you. It's two holes. I mean, there's two pieces of rebar. It would look just like, literally, it would look like two holes on top of each other like that because they would bypassed. I have not found this one time on that entire wall. Not once. Even with the fireman video on the outside, I look at the rebar. They all look like single rebar going over from the stressed on the walkway side. Single rebar. I didn't find one double bar. So, this is what I find really amazing on that wall there. We don't find the double bar. Nor do we find the double bar like this, one high, one low. Up here, I don't expect to see double bar. I would expect that double bar to be down here, engaged every now and then. It's 12 inches on center. If these were supposed to be 12 inches on center, you would engage it. The best place to engage it and space it would be right at the 90s. That would come out of here and over. So this is troublesome. Also, this detail is spec. The deck detail is spec like this. Just so you know, they have a 90 where this rebar comes down. It doesn't turn down, so it doesn't go far like that like I have it. It would probably stop there if you were doing it, and it would be a 90. It would be over there like that. But turn this away from us. Turn it 90 degrees away from us. Yeah, 90 degrees away from us, and you would see the engagement. I'm going to end this video. Just wanted to get this up there to help you get ready for the 1 hour and 8 video. I think I'm going to rechange the time on this. I had it going off in about 30 minutes. I'm going to put this one going off in about an hour, and then I'll bounce this one out to Saturday or something. I want this to soak in a bit. All right, take care, guys. Love you all. Oh, remember, the shear links, they don't have them. They don't do them. It would be great if they start doing them. ACI is not one to learn, to advance. It's like the same. If you want to know what ACI is all about, just look at them from the 1900s to current day. They take a long time to learn. It's like they're in a echo chamber of not learning. They just blaming contractors all the time, or it's faults here, but it's not. They refuse to increase their structural ability of things like this. It's like they stretch it out. Whatever.